Hi and welcome back to our course on modern manufacturing. In the last lecture, we learned about how we perceive manufacturing in the modern scenario, both technologically and economically. Now, before proceeding to the modern manufacturing processes and systems, we first need to know why they are needed. The need for new manufacturing processes was created with the invention of newer materials that fit into modern world. In this lecture, we will learn about what these materials are. We will first have a quick revision of the traditional materials that we have learned in our engineering books. Then, we will move on to the modern materials and their subcategories. Engineering materials are mostly solid-state materials that can undergo various manufacturing operations in order to be converted into the desired products. Most engineering materials can be classified into three basic categories: metals, ceramics, and polymers. Their chemistries are different, their mechanical and physical properties are different, and these differences affect the manufacturing processes that can be used to produce products from them. Metals are elements in the periodic table that display properties such as strength, ductility, high melting points, thermal and electrical conductivity, and toughness. In the industrial applications, they can be categorized as ferrous and non-ferrous metals. Ferrous metals are based on iron. This group includes various types of steels and cast iron prepared by alloying iron with carbon. Steels contain 0.2 to 2% carbon, while cast iron contains 2 to 4% of carbon. Is primarily used in sand casting. Non-ferrous metals include aluminium, copper, magnesium, nickel, titanium, precious metals, refractory metals, and their alloys. Let's discuss some of the common metals and their uses. Iron and steel alloys are used where strength is required, like production of railings. Aluminium and its alloys are used because they are easy to form, readily available, inexpensive, and recyclable. Aluminium is heavily used in construction and automotive industries. Copper and its alloys have a number of properties that make them useful, including high electrical and thermal conductivity, high ductility, and good corrosion resistance, making it the best choice for electrical wires. Titanium alloys are used for strength in higher temperature applications. It could be a temperature around 1000 degrees Fahrenheit when component weight is a concern or when good corrosion resistance is required. They find application in aerospace, marine, engine components, and cryogenic vessels. Nickel alloys are used for even higher temperatures between 1500 to 2000 degrees Fahrenheit with good corrosion resistance in storage batteries, anode and cathode, chemical and food processing equipment, and electronic and aerospace applications. Refractory materials such as niobium, molybdenum, tantalum, tungsten, and rhenium are used for the highest temperature exceeding 2000 degrees Fahrenheit. They have extraordinary resistance to heat and wear and are chemically inert. They are used in lighting, tools, lubrication, and inside nuclear reactors. That was all about metals. Now, ceramics are compounds of metallic and non-metallic elements. They are prepared when powdered materials are fabricated into products through the application of heat and display properties such as hardness, strength, low electrical conductivity and brittleness. Ceramics can have different segments like structural plate, which consists of fine particles of hydrous aluminium silicates and other minerals. It is used in bricks, sewer pipes, tiles, and flue linings. Whiteware, another type of clay used in dinnerware, floor and wall tile, electrical porcelain. Refractories are brick and monolithic products used in metal, glass, cements, ceramics, energy conversion, petroleum, and chemical industries. Glasses such as flat glass is used to make windows, container glass is used to make bottles, pressed and blown glass is used to make beautiful dinnerware, and glass fibers are used in home insulation, and advanced specialty glass is used in optical fibers. Abrasives can either be naturally occurring such as garnet and diamond, or synthetic ones such as silicon carbide and alumina. Abrasives are used for grinding, cutting, polishing, lapping, or pressure blasting of materials. Cements are used for roads, bridges, buildings, dams, and all kinds of construction. Advanced applications of ceramics include structural, electrical, coating, chemical and environmental purposes. Next, coming to polymers. Polymers are compounds of carbon along with hydrogen, nitrogen, oxygen, or chlorine. Polymers are primarily produced from petroleum or natural gas raw products, but the use of organic substances is growing. Polymers have many properties that make them attractive to use in certain conditions. They are less dense than metals or ceramics, resist atmospheric and other forms of corrosion, offer good compatibility with human tissues, and exhibit excellent resistance to conduction of electrical current. Two industrially important polymeric materials are plastics and elastomers. Plastics are a large and varied group of synthetic materials which are processed by forming or molding into shape. Just as there are many types of metals, there are many types of plastics as well. Elastomers or rubbers are naturally occurring materials. They can be elastically deformed to a large extent when a force is applied to them and can return to their original shape when the force is released. The polymer plastics can be further divided into two classes, thermoplastics and thermosetting plastics. Depending on how they are structurally and chemically bonded, thermoplastic polymers comprise the four most important commodity materials: polyethylene, polypropylene, polystyrene, and polyvinyl chloride. There are also a number of specialized engineering polymers. The term thermoplastic indicates that these materials melt on heating and may be processed by a variety of molding and extrusion techniques. Alternatively, thermosetting polymers cannot be melted or remelted. Thermosetting polymers include alkyds, amino and phenolic resins, epoxies, polyurethanes, and unsaturated polyester. Now, let's come to the main topic of this lecture: modern materials. A modern material is a material that has been engineered to have improved properties. For the past few decades, concrete, aluminium, and steel were commonly used modern materials, but more recent additions include materials that have changed the way we manufacture and use products. Let's discuss the type of modern materials that have been evolving in the market since a decade. Metal foams are a strong but lightweight modern material produced by injecting gas or foaming agent into molten metal. Typically, only 5 to 25% of the foam is metal, and this allows the material to retain much of its strength but without the density or weight of a solid metal. Metal foams are often used in vehicles such as planes and cars, as they absorb shock effectively if the vehicle crashes. Liquid crystals are between a liquid and solid state. When charge is applied to each liquid crystal, the shape changes to either block light or let light through. Liquid crystal displays use the light modulating properties of liquid crystals to display an image. This ensures text or images display on the LCD. LCDs require a backlight to work, and many modern devices now use organic light emitting diodes instead, which allows devices to be thinner and lighter. OLEDs are more expensive as each pixel is its own light, but they allow for thinner panels and better color and contrast. Phase change materials are substances that absorb and release thermal energy during the process of melting and freezing. They are called phase change materials because they go from a solid to a liquid state during the thermal cycling process. Hydrocarbons, primarily paraffin, sugar, alcohols, and lipids, are categorized as organic phase change materials. Salt hydrates are categorized as inorganic phase change materials. Abundant natural building materials are hygroscopic, which means they can absorb water. A subset of PCM goes through a solid to solid phase transition, absorbing and releasing substantial amounts of heat in the process. At a given and well-defined temperature, these materials alter their crystalline structure from one lattice configuration to another, and the transformation can include latent temperatures comparable to the most successful solid-liquid PCMs. Superalloys are a group of metals that offer better creep, oxidation, and corrosion resistance than traditional alloys, while retaining excellent mechanical properties even at high temperatures. In a sense, they act as high-performance alloys. Commonly used in the aerospace industry for components in gas turbine engines, superalloys use a base of nickel, cobalt, or iron to offer far superior properties versus traditional alloys of steel or aluminum. Let's take a quick look at a few commonly used superalloys. Hastelloy C22 and Inconel 625 are commonly used nickel-based alloys. X40 is a non-ferrous cobalt-based alloy. It is used mainly for its excellent creep resistance. A286 is a frequently used iron-based superalloy. It can be thought of as an evolution of stainless steel, offering the usual corrosion resistance only up to an extreme temperature of 700 degrees Celsius. Composite materials are made up of different materials which are combined to improve their properties. They can be a combination of natural and synthetic materials but fall into three main categories: fiber-based composites, particle-based composites, and sheet-based composites. Fiber-based composites are reinforced with fibers. By mixing resin or concrete with fibers of glass or carbon, we get the ability to mold complex shapes, but reinforcing them with the fibers makes them very strong. Particle-based composites are made with small particles of materials. By mixing smaller particles of sand with larger particles of cement and aggregate, such as stones, we get a very strong and dense material suitable for building large structures. Sheet-based composites are often available in large sheets. By mixing wood fibers or thin slices of wood veneers with resin, it is possible to form large and stable sheets for furniture panels and interior construction. Like all modern materials, composites are engineered to improve their properties. There are many more combinations of materials that are designed to meet a particular need or purpose. For example, wood has been reinforced with strips of carbon to make a wooden bicycle frame. Often, the original material has a useful feature like the ability to be formed or a certain appearance, but lacks strength or durability. In this case, different material combinations can solve the problem, and new composites are being developed all the time. Nanomaterials are usually considered to be materials with at least one external dimension that measures 100 nanometers or less, or with internal structures measuring 100 nanometers or less. They may be in the form of particles, tubes, rods, or fibers. The nanoparticles that have the same composition as known materials in bulk form may have different physico-chemical properties than the same materials in bulk form and may behave differently if they enter the body. The number of products produced by nanotechnology or containing nanomaterials entering the market is increasing. Current applications include healthcare in targeted drug delivery, regenerative medicines and diagnostics, electronics, cosmetics, textiles, information technology, and environmental protection. Oleophobic coatings are oil repelling, while hydrophobic materials are water repelling. They are often called self-cleaning coatings because of how they shed water droplets and resist greasy fingerprints. These coatings are used in mobile screens, eyeglass lenses, and cookware. Graphene is a single carbon layer material which is hypothetically 100 times stronger than steel. It is hypothetical because we are yet to manufacture it in large enough quantities to prove this. In theory, it could provide body armor that is bulletproof, invisible, and almost weightless. If the whole of Eden Gardens was covered in a layer of graphene, it would be almost invisible and be unbreakable, yet it could be all lifted with one finger. Silver nanoparticles have the ability to penetrate bacterial cell walls, changing the structure of cell membranes and even resulting in cell death. Nanosilver is appearing in a range of products including washing machines, socks, food packaging, wound dressings, and food supplements. Smart materials. While smart materials are modern materials are not necessarily smart. To be classed as a smart material, they need to exhibit a physical change in response to some external stimuli. In other words, they change when you do something to them. And when you remove what is causing that change, they return to their original form. Memory shape alloys are metal alloys that can remember their shape when heated. These alloys have been utilized in spectacle frames that spring back to shape when they are squashed. Nickel titanium, nitinol, is a type of SMA and it contrasts when heated, whereas most metals expand. When braces are made from nitinol, they heat up in the mouth and pull on the teeth, so they move with the nitinol. Thermochromic pigments change color when their temperature changes. The term thermo relates to heat and chroma means color. So thermochromic pigments change color when they are heated up. These pigments can be mixed with paint or polymer to give the materials the same color changing properties as the pigment. An example of this technology is seen on color changing mugs or buff items for children. Photochromic pigments work in a similar way, but photo means light. So these pigments change their properties when exposed to ultraviolet light. A well-known example would be glasses where the lenses are clear when worn inside a building but become more like sunglasses when exposed to bright sunlight outside. The same technology has been used in windows to prevent rooms from getting too hot in warm weather. Quantum tunneling composite (QTC) is an insulating rubber containing tiny particles of metal. When squashed, the metal particles meet and allow the flow of electric current. As a result, QTC is an insulator when resting and a conductor when pressure is applied. It is often used in outdoor applications where water might otherwise damage tiny microswitches. It has been used in clothing to control smartphones and portable music players, in power tools to give variable speed controls, and in touch-sensitive pads. Self-healing materials have the ability to repair themselves, which can extend the lifespan of the products that use them. These include polymers that can heal knife cuts in themselves, metals that resist corrosion, and concrete that can heal when cracked. Ferrofluids can be formed by a magnetic field and are being used in hydraulic suspension pistons, with the strength of the magnetic field allowing the suspension to be hard or soft depending on what is necessary. They also have friction reducing properties, allowing magnetic objects to glide across the surface. Polymorph is a polymer that becomes malleable when heated to about 62 degrees Celsius. When it cools down, it becomes hard enough to drill and cut. This makes it perfect for modeling as it can be reheated and formed again. It is also excellent for creating ergonomic handles. The last subcategory of modern materials is technical textiles. Textiles have come a long way from the early days of cotton and silk, and today's modern textiles have some very advanced and useful properties. A major advancement in textiles technology was the invention of polyamide, more commonly known as nylon. This synthetic material can be pulled into very thin strands when heated and spun just like natural textiles, and is now used extensively as a fabric in clothing. Modern textiles can be engineered to have numerous properties such as additional strength or resistance to fire, water, and even dirt. Conductive fabrics allow a small electrical current to safely pass through them. This technology is used to dissipate static charge or for touchscreen gloves, which allows a small amount of charge to flow through the glove to connect to the screen. Fire retardant fabrics are textiles that are more resistant to fire than others. Through chemical treatment or manufactured fireproof fibers. They are often used in furniture and furnishings where fire safety is paramount. Kevlar is a tightly woven fabric that has great impact resistance. It is used in racing tires, racing sails, gardening gloves, and bulletproof vests. Microfibers are much thinner than human hair and can be coiled to provide a very warm, soft, or absorbent material that can be used in winter clothes or products such as cleaning cloth. Microencapsulation involves encapsulating liquids or solid substances in tiny thin-walled bubbles. These microfibers gradually release active agents when rubbed, which rupture the thin-walled membrane. This can bring benefits such as smelling good to cover body odors in sports clothing. A similar technology is used in the scratch and sniff perfume and aftershave samples in magazines. Since the development of synthetic fibers, there have been numerous improvements in textile technology, and new variations are constantly being produced. Like other engineered modern materials, properties can be combined or enhanced. So, if you want something to be fire and water resistant while also being conductive, textiles can be engineered to meet those needs. This was all about modern materials. In the next lecture, we will discuss innovations in manufacturing process, production machines, and tooling. Thanks for watching this lecture. See you in the next one.